So a formal definition of limit. So this, again, it is a very formal definition of limit. Yesterday when we talked about limit, we kind of just defined it very briefly, sort of like it means that you're approaching a value, right? It was sort of this generic explanation. Today, this is the official formal definition of it. It says, let f be a function defined in an open interval containing c, except possibly at c itself, and let L be a real number. Then the statement, the limit as x approaches c of f of x equals L, means that, okay, so here's our new symbols. For every epsilon, that's what this is again, epsilon, greater than 0, there exists a delta greater than 0, such that if 0 is less than or equal to the absolute value of x minus c less than delta, then the absolute value of f of x minus L is less than epsilon. Got it? Okay, great. Let's move on. No, I'm just kidding. Okay, so what does that mean, right? Basically what this means is there's going, and when I do this next part here, I'm going to draw a picture, and it'll make a lot more sense here, okay? But what this means is that there's this little, around your C, okay, around your x value for C, there's going to be a little delta band on either way. And then around your limit, there's going to be a little epsilon band up and down from it. And as those bands get smaller and smaller and smaller, that's when we're approaching that limit. That's what that means. So we're picking really, really little values for these epsilons and deltas. And we want to figure out what those small numbers are that approach and get us as close as we can to that limit. Okay? That's kind of all that this really is talking about. So let me walk you through it. So let's say we have some function, right? Just something like this. Okay. And you have your x, as x is approaching c. So c is going to be down here somewhere. Okay, that's my x value. And this could be a whole, possibly, right? But again, that's where our limit is. And so the y value that corresponds to that is your L for limit. Okay? So what it's saying is that we can find such a number, epsilon, on either side of the limit. So it might be like 0.001. And I would add it to the limit, and I would subtract it from the limit. And so I would get this little, what we call epsilon band. And I'm going to, this is really like highlighted. A lot bigger than it really would be. Normally it's much, much smaller. And so what this is, again, is this little up and down is this E for epsilon. So this number on the top is L plus epsilon. This number on the bottom is L minus epsilon. Sorry, that should say minus. Okay? So it's this band around your limit, L plus epsilon and L minus epsilon. Does that make sense? So we have this little band. Well, corresponding to that band, there's got to be some C values down here, some X values that correspond to those Y values, right? Well, those X values that we're going to get are called our delta band. Okay? Hi, who do you need?
Mike?
Yeah, no, sorry. They're all in AP testing. So, can you roll his eyes?
Where's the AFC?
I don't know. So, again, does that make sense? That there's going to be for this epsilon value that they give you, and they're going to give you the epsilon value in the problem. They give you this epsilon value. For that epsilon value, there's going to be these corresponding now. Down here, there's these corresponding, okay, delta values. And so this little cursive D, that's my delta band. So this point here would be C plus delta, and this point right here would be C minus delta. And that would create my delta band. Yeah, we call these bands. Not exactly sure why, right? So this C minus delta and C plus delta, that's called your delta. Oh, I wrote the D fancy. That's called your delta band. And then over here, with this L plus epsilon, L minus epsilon, that's called my epsilon band.
Oh.
All right, so what the problems are going to do, I'm just going to go to my for a second. what the problems are going to do is they're going to give you a certain epsilon, and they're going to ask you to find the corresponding delta, okay? And what you're going to need to find is the largest possible delta band that works for it, okay? But it's not, that's what I wanted. But it's not necessarily, so you want to find the largest corresponding one. When this is a linear graph, it's going to be exactly the same. But if we've got some curves going on, it's going to affect, and it won't be exactly the same. So you're going to have to get the largest delta band, you're going to have to pick the smaller number. And I'll talk you through it when we go through the next example, okay? So let's do example 6. Everyone got that picture down? All right, so they gave you a function here. Okay. And so this is my f of x, 2x minus 5. And so we can graph this because it kind of helps to take a look at it, right? So 2x minus 5, 1, 2, 3, 4, 5, up 2 over 1, up 2 over 1. Right, so we have something like this. Right? So this is my graph. And they give us a limit when x is approaching 3. So that number down there, that's our c. So c is equal to 3. So when I'm at 3 here, what is this, 2? 3 is somewhere in here, right?
What?
X equals 3. Sorry. Oh, because down here, they told us as x approaches 3.
Oh.
So in this notation, right, x approaches 3, they're giving you the c. And then they tell you that the limit, this number here, this 1, that's your L, that's your limit. Well, that makes sense because that's the value of my function. Right? So it's the point is 3, 1. Okay? So then what they're going to do here, and they wrote it in this notation, they wrote f of x minus L, so this is just f of x minus L, is less than, now this number right here, if you go back up to that original definition, go back up here, f of x minus L, that absolute value of that is less than epsilon. So this number that they gave you right here, that 0.01, that's the epsilon. So they're kind of hiding it in there for you. Okay? So they gave you the function, they gave you the c, they gave you the L, they gave you the epsilon. Whenever 0 is less than the absolute value of x minus 3, again, there's your x minus c, which is less than delta. We have to find delta. Okay, that's our goal. Okay? So what's the epsilon band? Well, again, I'm going to take my limit. This was my limit. Okay? And I'm going to add epsilon to it, up, and I'm going to subtract epsilon from it, down. And that's going to give me the epsilon band. Okay, so your epsilon band is always L minus epsilon, L plus epsilon. So since L was 1, I do 1 minus 0.01, and then I do 1 plus 0.01. So I get 0.99, and I get 1.01. Okay, so those are, and you can draw it in your graph if you want to. You can kind of see where that is. So this is 1.01, and this is 0.99. So what I have to do now is I have to find the x values that correspond to those. So I just take that 1.01 and plug it into my graph and figure out what is the x value here. And then I have to take the 0.99 and plug it into my graph and figure out what is the x value there. Yeah?
So you could just do like minus 0.013 or plus 0.013?
Not from the 3, no, because it's the equation is 2x minus 5, right?
Yeah.
So what I have to do is I have to take this and set it equal to 2x minus 5. This is the y value, okay? So I'm going to take each of these and do 1.01 equals 2x minus 5. And then I do 0.99 equals 2x minus 5, because I'm trying to find the corresponding x value. Go ahead and solve each of those. So add 5, divide by 2. All right, so for x on this one, I got 2.995. And for x on this one, plus 5 divided by 2. You guys are all doing this with me, right?
Yeah.
3.005. So what did I just find? I found these x values. I found 3.005 here and 2.995 here. Okay? So those values then are giving me now my delta band. But they're not telling me what delta is. Because what exactly is delta?
It's 3,
It's-
it's 0.005.
It's the difference.
0.005.
Exactly. And in this case, it's the same for both because it's 0.005 to the right and it's 0.005 to the left. When it's the same for both, that's your delta, 0.005. Okay. When it's different, and that's what we'll see on the next page because it will be different if our graphs are not linear, we always pick the smallest one. Okay. So let me show you. So the largest possible delta then, all that you do to find delta, and you guys kind of just did this in your head, but really what the rule is here is to find delta, I do x minus c. It's really the absolute value of that. And so I took this x value that I got, which was 3.005, and I subtracted c, which was 3. And so delta is just 0.005. And you want to do it for both of them. Again, in this case, it's going to be the same. So I would get the absolute value of negative 0.005, which is still just 0.005. So since I get the same one for both, then that is my largest possible delta. And the band, we already figured it out, 2.995, 3.005. And we're done. Sometimes I'll ask you just to find delta. Other times I'll ask you to find the whole band. Make sense?
Yeah. Is it usually both like the same? Or
No.
is just
It will only both be the same if it's linear.
Okay.
So since my graph was just 2x minus 5,
Yeah.
nice and linear, it's going to be exactly the same on both sides. Next example we're going to do is a quadratic, not going to be the same on both sides. Okay? So we're going to have to then pick the smaller one. Yes, ma'am?
So is the epsilon always going to be the same thing?
Yes. They will always give you the epsilon.
What will they like ever start where they like give us the delta instead of the epsilon?
No. Not in what we're doing. It'll always be we give you the epsilon and you find the deltas. Okay, this next one was just another way to do it. I feel like we can skip that because we don't really need another way to do it. I think we're good. I think it makes sense. So let's go down to B and show you the example with a quadratic. Okay, so this top part you can just ignore. All right, so B. So notice we have a quadratic now. Okay, so it's not going to be the same on both sides. So let me kind of walk us through this one. First thing I would do is I would graph this. X squared plus 1. Okay, so that's just an x squared graph that's been moved up 1. And we're looking at it as x approaches 2. So, you know, I'll graph it 1, 2, 3. Okay, so at 1, I'd be at what? Here, 2. At 2 squared 4, I'd be at 5. Okay, and so this would be my graph. Something like that. Pretend that looks like a parabola. We're on B. Yeah, we skipped A. We skipped A. We're down B. Yep, there you go. Now you're good. Okay, so there's our graph, and we're trying to find the limit as x approaches 2. They told us the limit is 5. Oh, so that's nice. So what have they given us? Let's talk about what they've given us. They've given us C. C is 2. Okay, and they've given me the limit, which is 5. Well, obviously, that's the value of my function. So that's obviously my limit right there in this case. Okay, there's no holes or anything weird. And then they gave us an epsilon, 0.001. So I'm going to add a 0.001 and subtract a 0.001 to get my epsilon band. Okay, so it's always L minus epsilon, L plus epsilon. So when I subtract it, what was L again? 5. So 5 minus 0.001. Just be really careful with your decimals because sometimes it's like 0.01, sometimes it's 0.001, sometimes it's 0.0001. Okay, so just be tricky with those and make sure you found the right thing. So 0.499999. And then if I add it, I would get 5.001, right? And so now what do I have to find? I have to find the corresponding x value. So when I go in here, I want to find what is this x value that corresponds to a y value of 4.999. And then similarly, I want to find the x value over here. Okay, I want to find those two x values. So I just set my function, x squared plus 1 equal to 4.999. And same thing over here, x squared plus 1 equal to 5.001. and I solve for x. Keep all of your decimals with you the whole time. No sig figs. Okay, so this is where, right, you get 3.999. When you take the square root of both sides, you get this really long number, right? Sorry, my thing died. Okay, I get this really long number. So I get what? 1.999749984. And when you do the same thing over here, right, minus 1, x squared, square root, big, long answer, 2.000249984. So that's this value here. That was that 1.999, blah, blah, blah. And this was the 2.0002, dot, 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 dot. Okay. So the issue is here I have to find delta. Well, delta is the distance away that these values are from 2, right? It's that, what's the delta here, what's the delta here? These two deltas are going to be different, right? Because this is a quadratic, this one's going to be a little closer, this one's going to be a little further. They're not going to be exactly the same. In order to find the largest possible delta band, to make sure that it always falls within that delta band, we call it the largest possible. The irony is we're going to take the smallest number. So you're going to calculate these two deltas, and then you're going to pick the smaller one to give you the actual delta we want. Why would I pick the smaller delta? Because if I pick the bigger delta, right, what's going to be the problem? If I picked a number all the way out here at the end, right, and I tried to plug it in on this side of it, I said that was my delta band, is that going to fall within my epsilon? No, because I'm going to be too far out. Does that make sense? So I have to pick the smaller one to make sure that all the values are going to fall within the epsilon band that I was given. All right, so figure out your deltas. So delta is just the absolute value of x minus c. What was c again? C was 2. So I take the absolute value of this big long number, 1.999, and you should just keep it in your calculator. Subtract 2 from there, and what do you get? 0.000250016. Let me do the same thing over here. And this is why you got to keep all this in your calculator. So x, oh, I did this the other, oh yeah, you're good. 2.002 minus 2, right? Dot, dot, dot. But use the one in your calculator, and you should get 0.000249984. So this is the one that's smaller. Okay? And so you're always going to pick the smaller delta. Always pick smaller delta. Okay. Now what were we supposed to find? Oh, we're supposed to actually find the delta band. So we didn't actually find the delta band yet. So we're told you're not done. So the delta band with this new delta now is x plus delta, x minus, or c plus delta, c minus delta, right? So to actually find that band, I need to do c minus delta, c plus delta. It's a lot of calculator stuff. Okay, so c is 2 minus 0.000249984. So this one is 1.99975, right? And then c plus delta, we actually had c plus delta because that was the one we picked right up there, right? So that was the same one. 0.000249984. So this is my delta band. Okay. So just a note here at the bottom, this epsilon delta definition of limit is used to prove theorems about limits. This is sort of much higher level calculus, and to establish existence or non-existence of certain limits. To finding them, we just need to use these techniques of actually just given an epsilon, find delta. That's all we got to do for this class, for what we're using it for. Okay? Questions? All right, let's practice a little then. So turn to, no, I'm going to help you do some of your homework. Page 9. Let's work through them. So page 9, your homework tonight is page 9 and some other stuff. Let me look.
Just page 9.
No. For tonight? Tonight is page 9, 10, 11, and 12. 9, 10, 11, and 12. And 11 and 12 are just more epsilon delta, and so is 9. So let's try and do page 9. 9, 10, 11, and 12. So if you get done with 9, then all you have is 10, 11, and 12. Doesn't that sound good? But 11 and 12 are actually only 4 problems. It's like they're really big. Okay, so don't worry about it. Here we go. Am I doing these with you, or are you doing them? Yeah. Am I doing these with you, or?
Yeah.
Okay, number 1. Okay, do it by yourself. He doesn't want me to do it with him. Sometimes slower.
Don't tell me I forgot my
Epsilon band, you got this, right? Okay, how about this? I'll work it out up here. If you need help, just look up.
I don't want to get on my calculator.
Yeah, you're going to need it, sorry.
How do you find the first?
Which first line is that?
No,
So they gave you down here, the number they give you, x approaches. That's your C.
yeah.
This is your L. So that's C. That's L. So 2, 5. And it'll always be a point on your graph for these ones. Okay? Oh, these are nice. It just asked you for delta, not the whole band. Done with number 1. The first 2 are linear, so they're a little easier. The next 2 are quadratics. Do we need help or no?
May the curve be over your church.